Alright, so we're back. And today we're going to talk about what gas laws have to do with chemistry. Because besides putting some chemical names in problems so far, I haven't really felt like gas laws are chemistry. I mean, my friend the mole is missing. And if we're going to talk about the mole, then there's no better place to start than with the man, myth, and legend himself, Avogadro. And Avogadro, believe it or not, has his own gas law, which is that equal volumes of gases at the same temperature and pressure have equal numbers of particles. That's actually really surprising to me. That different gases, as long as you have the same temperature, pressure, and volume, have the same number of atoms in them, the same number of molecules, the same number of formula units, whatever you're working with. A question. This is why we could make Boyle's, Charles, and Gay-Lussac's together into the combined law. It's because this is true. The mole is the thing tying those things into the combined gas law. If we look at them, there's always a constant. This explains why. Avogadro's principle doesn't have an equation in the same way Boyle's, Charles, and Gay-Lussac's does. Instead, it has a simple fact we need to consider. And that is, at 1 atmosphere and 273 K. That has a special name. What is it? So at STP, a mole of any gas, per Avogadro's principle, occupies the same volume, 22.4 liters. So if you have a mole of gas, you have 22.4 liters of it at STP. I'm going to throw a couple of pictures on the screen here of what 22.4 liters looks like so you get an idea. So 22.4 liters is this beach ball, or this jerry can for water, or the amount of water in this 6-gallon fish tank, give or take. So let's say I've got 3 different containers, one with helium, one with nitrogen, and one with methane. And all of these containers are the exact same volume, 22.4 liters. Now if I keep them at the exact same pressure and temperature, that is at STP, then each of these is going to have a molar mass in grams in it. So even though these have the same temperature, pressure, volume, they weigh different amounts. They have a different mass. But what's constant between them, why these 3 things are equal, is the fact they all have the same number of particles, right? This has 6 to the 23rd of methane, this is 6 times 10 to the 23rd of nitrogen, etc., etc. And so this is really powerful. It's also really easy, because this is just a conversion factor, like we've been doing with pressures. So that lets us set up a simple problem. Alright, so this question asks, how many liters does 9.5 moles of gas occupy at STP? It doesn't matter what gas, it doesn't matter its molar mass, not yet. At STP, how many liters does this occupy? Well, let's see, I've got 9.5 moles, and I'm just going to set up a conversion factor. So moles is currently on top. So because moles is on top, where does it end up here? Which means the other term has to be liters, right? The question asks for liters, and the unknown goes on top. So let's see. I've got a conversion factor here, right? I know there are 22.4 liters per mole, per 1 mole. Hey, look at that. It's not a bad problem to set up. So I type that into my TI-34 here, and out comes 212.8. Now, technically, my best answer would be 210 because of sig figs, but the conversion factor is still the same. Sorry about that. So that's not so bad, actually. It's just using a conversion factor. And I can flip that conversion factor over to go the other way. Let's set this problem up together. My known is 44.8 liters. So where does liters go, top or bottom? And now my conversion factor, 22.4, goes with liters. So does 22.4 go on the top or the bottom here? And of course, 1 goes with mole because there's no number given in the denominator. So check it out. That's really easy. I've got 3 sig figs here. Throw this through my calculator, and I'm going to get 2.00 moles. Great. These problems are pretty easy. I could throw a curveball your way, though. I could throw you a question like this. What volume would 2 kilograms of methane have at standard temperature and pressure? So there's a lot to decode in this question. For 1, kilograms isn't going to work. This is 2,000 grams. And STP, that's a key word for us. We really need to notice that. Okay, so I know that I have 22.4 liters per mole, but I don't have moles here. I have grams, so I need to turn this into moles. So I need to find the molar mass of methane, if I didn't know that off the top of my head, which is 16, but let's prove that. So I've got the molar mass here. So I'm going to take my known. Hey, grams on the top. Where's it go again? And it looks really familiar because it is. It's just what we've been doing all year long. Find the number of moles with some quick division. And apparently, I have 125 mole. But that's not what I asked. I asked about volume. Will volume be measured in liters, atmospheres, or Kelvin? So all I have to do to get those liters is just multiply by 22.4. So I do that, and I get 2,800 liters. For those of you in Soli's class would want to signify that as significant. Ignore it if you don't recognize what's going on there. It's no big deal. Doyle and I talked about it right at the beginning of the year. I don't know if Doyle still has you write them that way or not. Anyway, 2,800 liters. That brings to mind a question. Why did I write this question that way? I think a couple pictures here will answer that. You see, cows make a lot of methane. Like 2 kilograms of methane a week. And we know that because scientists drill holes into the side of the cow and collect the gas in a bag. As a matter of fact, here's the gas collected from a cow in an hour by a group called the Royal Institute. They're in London, a very famous chemistry group. And he's going to ignite it with a torch. So let's see how much energy is in the cow burps and farts in an hour. Every hour, every cow, it's a lot of energy in there. And a lot of methane, which is a problem because methane is a very potent greenhouse gas. Much more powerful than carbon dioxide, like 20 times more powerful. So actually the cow burps, because most of the methane is emitted by burps, is actually a huge part of current atmospheric and chemical research in trying to understand how cows impact climate change. And just being clear, cows actually do play a major factor in climate change. So when you come around to do the homework on Monday, STP is really your friend. It's the thing telling you, you can use 22.4, which leads to a key question. What happens if my gas isn't at standard temperature and pressure? Because, let's face it, 0 degrees centigrade is relatively rare, right? It's freezing point of water. And 1 atmosphere only really happens by the ocean. So what if I'm not by the ocean in a freezer? What if my gas isn't at that standard temperature and pressure? The answer to that question is one of the favorite equations of most chemists, Puvnert, or as it's known, the ideal gas law. Puvnert is the reason we've been doing gas laws up until this point. Now, each of these things are variables, so let's figure out what they are. P should likely stand for what? And V is a volume. Hey, as a question, which of these things isn't a volume? N is weird. N stands for moles in this equation. R is a new idea called a constant. We'll deal with him in a minute. And T is temperature. What unit would temperature need to be in? So here we have Puvnert. And it relates all of our variables together and allows us to use moles at different temperatures, volumes, and pressures. And the only thing relating them is apparently this letter R. Let me clear my desk for a second. I'm not going to make you do this, but let me show you what R actually is. So I've got Puvnert, PV equal nert. And I need to get R by itself. So I need to divide this side by NT. And that gives me a new equation. PV divided by NT equals R. What this means is that for any pressure, any volume, any number of moles, and any temperature, if I put them together and divide them, I will always get the same number. Assuming my measurements here are good and my gas isn't weirdly behaved. And that's what our boy Avogadro actually discovered, at least the foundation of it. That's why his principle works. Now, this is incredibly powerful if we could figure out what this number R actually was. If we were in a lab, maybe we could play around a little bit and try it, but we're not. So I'm going to give it to you. And that is that R is always, for this class, 0.0821 liter atmosphere mole Kelvin. This vomit of a unit at the end. Now, that in itself is useful, because that means if I plug this number into PV equals nRT, it's going to work out. That also complicates things, though. Let me show you why. So I've just written out the 5 variables in the equation here. And we already know that R is always what number? Always. The trick is, this is only true if you use these units. So yes, this big thing is here. You don't really need to write it in your equation to show me you know what you're doing. But your equation has to be converted to take these units. So, which of these 4 things is a pressure? And we know our temperature has to be in Kelvin. So, what does N stand for? Would it be liters or moles? This has to be true to use the ideal gas law. If you don't use these exact units, R won't work and Puvnert won't work. The ideal gas law breaks unless you use atmospheres, liters, moles, and Kelvin. Now, Kelvin, we're already well trained on. N doesn't have other units, so it's really only the P and the V that really trick students up. But if I gave you an equation in torr, if I said blah de blah de blah at 320 torr, could you use 320 torr in this equation directly? Before we go on, I want to make one quick point, and I want you to take a look at how this comes to be for real. Because I think understanding where Puvnert comes from is actually a big deal into why we're going to spend longer on it than any other gas law. Let's clear my desk really fast. Alright, so I want to look at this unit more carefully. We have pressure times volume divided by the temperature times the moles equals our constant. But this gives us an idea why the ideal gas law is so incredibly powerful. Because within here are all the relationships we've already learned about. Like pressure and volume, those things are related, right? Because we call that relationship the Boyle's relationship. And if you keep going through, you'll find other relationships. Like here, pressure and temperature, that's Gay-Lussac, right? Or here, the relationship between temperature and volume, which we call Charles' law. And we just said that volume and moles are related by Avogadro. And even more, you know there's a special relationship where pressure, volume, and temperature all change at once. Which law is that again? So in that one letter R, all of the relationships we've learned so far are actually present. And that lets the ideal gas law really, really work with gases in real life. And it makes it very easy. As a matter of fact, assuming an ideal gas, saying, oh yeah, this is true for this gas, is one of the most relieving, easy things to do in chemistry and in physics. And if you were to go farther into the sciences, you'll find when people tell you, oh yeah, you can assume this is an ideal gas, it's just like a giant hug. So much so that we like to make memes about it. I never said that chemistry memes would be any good. I mean, what else would you expect? But like, the ideal gas law is so relieving. Like, honestly, it's just a hug. And we like the ideal gas law so much that we're willing to use it to poke fun at probably the most important moment in modern science, the discovery of a first photograph of a black hole by this group of scientists here, who inevitably will win a Nobel Prize. That being said, for now we're done talking about the ideal gas law as an idea. On Monday we'll go into some examples of using it in real life, and then move into actually doing some practice. So it's a little longer to learn than the other gas laws. But for now, you have no homework this weekend, so I'll see you on Monday. Be gentle y buen camino en todo.